today I'm pleased to introduce the session's time series to vectors, leveraging InfluxDB and Milvus for similarity search. And our guest speaker is Anais. She will talk about time series to vectors. And Anais is a developer advocate for Influx Data with a passion for making data beautiful with the use of data analytics, AI, and machine learning. She takes the data that she collects, does a mix of research, exploration, and engineering to translate the data into something on function, value, and beauty. When she's not behind the screen, you can find her outside drawing, stretching, boarding, or chasing after a soccer ball. Welcome, Anais. The stage is yours.
Thank you so much, Stefan. Welcome, everybody. So today we're going to be learning about how we can transform time series data into vectors so that we can store it in Milvus and actually perform some similarity searches on that time series data so that we can handle, time series data with any other type of unstructured data and combine them together for some imaginary use cases. And this talk will include a quick demo running through a Jupyter notebook for how we can do that and actually convert the data. And it will serve to be just kind of an introduction on how you would do this, so that you could apply the same logic to whatever data you're actually storing, whatever time series data you're actually storing, and leverage it with something like Milvus together. So as Stefan mentioned, my name is Anais Georgiou, and I am a developer advocate at Influx Data. Influx Data creates InfluxDB, which is a time series database and platform. And I want to encourage you to also connect with me on LinkedIn if you want and ask me any questions about today's presentation, about time series forecasting, time series language models, statistics, databases, yeah, all thing time series. So please feel free to reach out there and connect with me if you want. But today we're going to be first talking about InfluxDB and learning a little bit about what that is, with the assumption that if you're here for Milvus, maybe you know a little bit more about Milvus already. And I'll talk about time series databases in general. Next, we'll move on to talking about time series databases versus vector databases. And quite frankly, this is kind of comparing apples to oranges. They're pretty different, but I think it can be useful just to compare the two to better understand each one. Then next we'll go into some various projects that you can try for yourself. I just wanted to introduce you to some resources and some projects if the time series forecasting and machine learning space interests you and you're looking to do something with time series, but then maybe also something with your unstructured data, and see how you could maybe fit that type of data into a project together. Then we'll go over a demo and we'll talk about leveraging InfluxDB and Milvus for similarity search. And for this, we'll use an imaginary use case where we're trying to find some anomalies within traffic data. Then we'll talk about some use cases for InfluxDB in the machine learning space, just so that you have a better understanding for some of the spaces that I work in more specifically. And I don't think we'll go through the tools that you can use for tasks such as machine learning and data processing, but we might. So that's a maybe. So yeah, let's get started. Introduction to InfluxDB and time series databases. So in order to understand InfluxDB and time series databases in general, the first thing that you need to understand is what is time series data. And time series data is any data that has a timestamp associated with it. So the earliest and maybe simplest example is stock market data. And one interesting thing about time series, or one thing that makes it unique, is that a single value is not interesting like it is with relational data. Instead, you're looking at the trend of data over time, and that helps you make decisions like whether or not to buy or sell. And that also makes time series interesting from a statistical perspective, because most data with an X and Y axis, you think of the X axis as being the y-axis or y variable as being independent, but in time series it's actually dependent, and so that means that has all sorts of repercussions and effects on how you analyze the data and what sort of forecasting and anomaly detection tools you need to use. Other examples of time series data include anything from the IoT space or um, the virtual world. So in the IoT or sensor world, you can think of time series data coming from sensors like pressure sensors, temperature, humidity, concentration, light, flow rate, etc. Like anything that you're measuring about your physical world, that is all IoT data, and that's all time series data. And then we apply the same logic to the virtual world as well, but virtual concepts related to software development. So we think of application monitoring, infrastructure monitoring, DevOps monitoring, and just wanting to understand trends in time about their virtual or physical environment. So we like to categorize time series data as two different types. The first is metrics, and metrics appear at a regular time interval. And the second is events, and events are unpredictable, and we cannot really determine when an event will occur, but we can still store event data all the same. So in the healthcare space, your heart rate would be a metric, and a cardiovascular event like an AFib or a heart attack would be an event. But one interesting thing between the two types of time series data is that we can transform events into metrics. So if we count, how many events we have, let's say in an industrial IoT scenario, maybe we're looking at how many machine faults occur daily, then this metric will either be 0 or more. And so we get now a metric from our event data. And so this is something that InfluxDB is also very good at doing. Additionally, time series data occurs in really every industry. We see it in manufacturing. Like I said, we're monitoring machines and we're doing things like predictive maintenance. We see it in renewable energy, from power consumption to production of that renewable energy. We see it in developer tools and APIs. You think about how many times a user triggers a specific request, for example. In Kubernetes, we have pod and application monitoring, and we even see it in gaming application. You can think of monitoring gaming servers. You can look at trends in gamer activity, wanting to reduce latency, and then of course in network monitoring as well, and SNMP monitoring. So we also see time series rising as a category, although we now see the new cool kid on the block is vector databases. But nonetheless, time series databases are also rising for this reason, just because time series data is part of so many different use cases. And it really emerged originally, we had relational data, and that's really great for orders and record retrieval. But it's not really good at handling requests for really large volumes of data. And then we got document databases that are really high throughput and have that adaptive schema, but they are space and resource intensive. And then we have search databases, and those are great for searching logs and other text-based time series data, but can be kind of slow for metrics. So that's why we see the emergence of time series that are specifically meant to handle event data, metric data, logs, and traces, as well as spans too. So what is a time series database, and what is it good at? What are some of the components or pillars that comprise a time series database? Well, the first is that it can accommodate and write timestamp data. That should be kind of a given. Every point in a time series database is associated with a timestamp. It's indexed and ordered by time so that you can query in time order and actually return your data with meaning. Then it also has really high write throughput. So if, for example, we were looking at a industrial manufacturing, maybe we're looking at monitoring some machine or a belt, and we have a vibration sensor. A industrial vibration sensor has a really high throughput, something like 1 to 10 kilohertz of data per second. So that's around up to 10,000 points per second of data that you are writing into your time series database. And if you are monitoring several pieces of equipment that have vibration sensors, let alone all the other sensors that you have in one single plant, you can see how you quickly have hundreds of thousands or maybe millions of points per second that you need to write. Additionally, if you can write a bunch of data to a time series database, but you can't query it, it's not very useful. So you need to also be able to perform really efficient queries over time ranges. And you also need to perform aggregations over those time ranges. You want to be able to find things like local and global minimum and maximum. So that means that you need to be able to perform really fast scans across your data as well, so that you can actually get those points returned to you. And then last but not least, this is not unique to time series databases though, scalability and performance, right? You need a scalable architecture, something that's designed to scale horizontally to handle any sort of increased load across distributed clusters of machines. And so this is what InfluxDB 3.0 looks like. It is our architecture diagram for 3.0. One fun fact is that the open source 3.0 is going to be out in January, so I'm really excited about that. But it's all built on the Apache ecosystem. So it's built on Data Fusion, and Data Fusion is the query execution framework. It allows users to query InfluxDB with both SQL and InfluxQL. InfluxQL is just a SQL-like query language that's proprietary to InfluxDB. And then it's also responsible for pruning and pushdowns to make those queries really efficient. Then we also have Apache Arrow, and that's our in-memory columnar data format. And Parquet is our durable file format that's also columnar. And so one reason that we are committed to being a part of the Apache ecosystem is to be a part of that open data architecture. So that just means that we are able to have more interoperability with other tools that leverage things like Parquet, that leverage things like Arrow and the Arrow flight clients, so that we can easily pull data out of InfluxDB and use it with other tools. A lot of machine learning tools leverage Parquet directly and operate on Parquet files. And so unlike, some data historians where there's a lot of vendor lock-in, one of the main goals with InfluxDB 3.0 is to allow you to pull and query, Parquet files eventually directly out of InfluxDB so that you can leverage them with whatever tools you want to. And then also additionally, just being a part of the Apache ecosystem means that we are continuously contributing to those upstream technologies and being a part of that larger community, which then enables not only other companies to take advantage of the contributions that we've made, but also just have interoperability with all the other tools that leverage them as well. So now let's talk about vector databases. So hopefully you are familiar with vector databases already, since you're here for a webinar on Milvus. There are a lot of vector databases, and vector databases are definitely the new cool kid on the block. So they are databases that specialize in handling vector embeddings, which are used in applications like machine learning, search engines, and recommendation systems to represent and compare really complex data, textual data, video data, etc. So we have, Milvus, of course, which is an open source vector database, and it supports both proximate nearest neighbor search, ANN search, and exact search. Then we have Pinecone, we have Weaviate, Face, which is created by Facebook, Annoy, various other vector databases. But not very many are open source, and I found Milvus very easy to use. So now I want to take a moment to just kind of compare and contrast time series databases versus vector databases, just so that we can have sort of a broad understanding of some of the differences between the two and also just how they work. And just generally as well, before I move on to that, I do want to take a quick second in case you aren't familiar with how vector databases work. Basically, the first step is representation. So whether or not you are working with data that's like text or images, first you transform that data into a vector. And then for text, that could mean that you're using some sort of model that converts each word or maybe a sentence into a vector based on the meaning of the words. For images, it could mean, extracting features like edges or colors or textures and representing those as a vector. And then you store those vectors in the vector database. And unlike traditional databases that store data in rows and columns, vector databases are optimized to handle the really high dimensionality of vectors. And then you use indexing to make the search more efficient. So the database builds an index based off of these vectors. And indexing is all about organizing the vectors in a way so that the similar vectors are located near each other in the database's storage system. And that's using special algorithms like ANN and stuff like that. And then finally, you perform searches on that data. So when you want to find data that is similar to the data that you're trying to query, like finding images similar to a particular image, you can think of like facial recognition, for example, that query data is also converted to a vector. And then the database uses that index to quickly find vectors that are closest to the query vector. And closeness here is how we measure a distance. And literally, we're doing something like an Euclidean distance. So that's in a nutshell how vector databases work. But now let's talk about the difference between the two. So time series databases. I talked about these use cases already. They are monitoring real-time use cases. So we're looking at tracking data over time. We're looking at monitoring service performance, financial market trends, or environmental sensor data. Some of the advantages is that they're optimized for time series data, allow you to query data over time and handle really large volumes of sequential data effectively. Also, You can perform time-based aggregations and perform fast scans over the data to find min and maximum counts, averages, etc. It also enables you to do really fast inserts and queries. Vector databases, very different use cases. You're performing similarity searches, so that's ideal for scenarios where you are trying to find items that are similar to a given query, image search, recommendation systems, or document retrieval based on content. And they're also used for machine learning and AI, so useful in applications involving really complex data models where you have these embeddings or vectors and you are representing them in this high dimensional space for tasks specifically like clustering and classification. So now I want to talk a little bit about how we use machine learning with time series databases and how we use machine learning with vector databases. So machine learning with time series databases would include things like forecasting, predicting future values based off of past series. So, you're forecasting sales, you're forecasting weather conditions, you're forecasting heart rate, etc. You also might be doing things like time series classification. You're identifying categories or events based off of historical time series data, like you're trying to classify whether or not you have an anomaly in your machine data um, for predictive maintenance, for example. Then we also have anomaly detection in time series data. So, in general, trying to detect unusual patterns which do not conform to the expected behavior. So, you're identifying spikes in network traffic that could maybe indicate a cyber attack or any sort of anomaly that you might have in your time series data. And then you're also frequently doing things like performing regression analysis. So, you're modeling the relationships between variables over time. And you might be looking at something like the impact of marketing spend on sales and various correlation analysis as well. And then machine learning with vector databases looks like performing similarity searches, which are used for recommendation systems, clustering to organize your data into clusters based on their similarity, which can be useful in things also like customer segmentation, in grouping similar documents, and finding related products. So things like similar to recommendation systems. And then anomaly detections as well, by measuring exactly how much data or a vector deviates from the norm of a cluster, you can then identify outliers in your data set. And that can help you in detecting things like fraudulent transactions or unusual user behavior. You also perform things like nearest neighbor classification or really any classification. That was just one very common example of um, a classification algorithm like KNNs to classify new data points based off of the most similar training examples that are stored in a vector database. So, kind of just to summarize here, vector databases and machine learning, they're best suited for applications where the core requirement is understanding the relationship between data points in a vector space. And for time series and ML, it's best used for applications where data is inherently sequential, time-stamped, and the tasks are revolved around understanding the trends, changes, anomalies, and forecasts over time. But that doesn't mean that we can't use them together. So I want to share with you kind of some projects that you can try, particularly one with about actually vectorizing time series data, um, so that you can use it with something like Milvus, and just in general talk about some use cases where you could use time series with Milvus. So the very first thing that I want to show you is the Python client library, because if you are writing any data to InfluxDB, um, I'd highly recommend that you use it, especially if you are wanting to combine it with Milvus, because you'll want to do some data transformation to actually convert that time series data into vectors so that you can use it with Milvus. So what you would do here is you would first import the library. Then you would specify your host, your org ID, your token, and your database. You'd instantiate the client, providing those credentials. Then you would query your data. Or similarly, you could write it with the write method instead of the query method, and you would pass in your data frame into the data frame option, and you'd be good to go. And then you'd write a data frame as well. But this is also how, once you had your data in InfluxDB, how you would query it out and then go ahead and leverage it with Python to do some of this data transformation required to make vectors out of your time series data. so that then you can use it in a similarity search with Milvus. And this is what the InfluxDB UI looks like. It's pretty easy to use to create a bucket. A bucket is basically just like a database where you'd store your data. You'd go to the buckets tab in the load data page. You'd hit create a bucket. You'd give your bucket a name and a retention policy, and this determines when your data is automatically expired, because with time series data, you frequently only care about the current data. You don't care about older data, and so you want to be able to automatically expire data that is too old. And so you'd include that retention data preference, 30 days or whatever it might be. Give it a name, hit create, you have a bucket. And then your org ID would be found right in the URL right here. That's the fastest way to find it. So that's what I always recommend there. And then similarly, to create a token, you can just generate a token. You can create a custom token to scope it, to give permission to particular buckets, whether it's read or write, up to you. So with that being said, let's talk about how we can transform time series into vectors. So you can follow this QR code or the URL below. It will take you to this community, Influx community organization on GitHub. And the Influx community organization on GitHub contains a bunch of different examples for how to use various technology stacks with InfluxDB. So if you're interested in doing just any time series forecasting or anomaly detection, or using InfluxDB with a variety of different tech stacks, I highly recommend that you come here. It's also where our client libraries are maintained, but we have projects around, creating a stock tracker demo. This, my coworker Suyash just made this to track stock data and do real-time analytics with it. We have a whole bunch of Grafana examples. We have fake factories that mirror beverage manufacturing companies and all of the sanitation and bottling not robots, bottling, wow, I just, like, my brain just died, all the bottling machines, thank you,
Yeah.
uh all the bottling and sanitation machines, almost directly from uh a real life customer, at almost at scale. So that's another cool project. We have some of my other favorite projects include, getting started with MQTT and various simulators there. I recently made this other project that mirrors how to use Kafka and Faust to simulate a PID controller for a continuous stirred tank reactor, which is a common type of chemical reactor used in chemical engineering and manufacturing, to both like to create a digital twin and actually use a controller. So long story short, there's a bunch of different projects worth checking out here if you want to do anything with time series and you want to get in the weeds there. But let's talk about the Milvus project today, because that's what we're here for. So basically, to run this, it's really simple. You're just going to go ahead and clone this directory into your machine, and I've done that already. I just need to run the Docker compose. So I guess I'll share that with you there. So I'm just running Docker compose up to start an instance of Milvus, and then I can create a new tab and simply run Jupyter Notebook to actually get that notebook up and running.
It was still on the terminal, by the way.
Okay, thank you. And I will now share my screen to go to the right tab. Perfect.
Yes.
So this is the notebook for running that, and I will go ahead and clear all the outputs real quickly. Perfect. Okay, so basically in this, also, is it big enough? Can you see it well?
Yeah, it's fine. Totally fine.
Okay.
Thank you.
Okay. Yeah. So basically this notebook will just demonstrate a workflow to process sensor data. And actually, let me come back here. So this is kind of the imaginary use case that I created for an excuse to vectorize some time series data. So it kind of helps us better understand the relationship between time series databases and vector databases, and it can just be helpful in this imaginary use case to contextualize how you might use the two together. So let's imagine that we're developing a platform that offers a real-time traffic monitoring and pattern recognition to improve city traffic management. So specifically what we want to do is we want to create a solution that identifies when traffic conditions are operating anonymously, oh my God, anomalously, thank you, brain, it's not on
Good
today.
morning.
I I need some anomaly detection for my own brain today, and determines like what type of traffic data, what type of anomaly we actually have present. So in this example, we might be storing things like speed limit, and actual position of cars and traffic to InfluxDB cloud, and that's our actual sensor data, where we're getting things like vehicle count and speed, etc. And then in Milvus, we are actually storing, maybe when we have seen anomalies present previously, some of those anomalies in Milvus. And so that way, when we detect that our data is out of norms, maybe with a really simple, um, parameters that just say like, hey, our normal statistics are off, then we can take some of that time series data and then vectorize it and compare it to some of the previous anomalies that we've seen in Milvus and actually determine what type of anomaly we have. So is it an accident? Is it just traffic? Is it construction, etc.? We could also imagine some other use cases where we would maybe combine time series data with other types of data that's typically stored in vector databases. You can think of the healthcare space, for example, where maybe we are monitoring different elements of a patient, things like their heart rate, their oxygen levels, etc., but then combining that with textual data based off of doctor's notes, and the long-term health of a patient, and also maybe also even images, things from radiology, etc., to combine all that data together to kind of make predictions about the state of a person and any upcoming illnesses that they might have based off of the similarity between their health records and other patients. um, so that being said, let's go back to the notebook. Okay, so I talked kind of about the imaginary use case for this. That being said, this notebook is really just intended to get you started vectorizing time series data as quickly as possible, not actually demonstrate with real data. So as a result, the very first step that I have is to just import your dependencies. And one second. There we go, I lost my screen. And so I'm using pandas and numpy here, just for the data manipulation and for the numerical operations. Importing date time so that I can work with timestamps and actually convert my timestamps to Unix so that I can basically normalize the timestamps and actually write them into Milvus, because Milvus doesn't support a timestamp format. It supports float and integers, so that's what you need to work with. And then we use matplotlib just to plot some of the data here so we understand what we're working with. And then last but not least, we're using PyMilvus, which is the Milvus client library to interact with the Milvus database. So I'm going to go ahead and import that first. And then I'm going to define a function to generate some traffic data here. So like I said, we're just generating some random speed limit, vehicle count, and average speed data so that we can generate a data frame with those random values. And if you're running this yourself, have something to work with that might look like data that you're working with so that you can easily learn how to vectorize it yourself. So specifically, we have these timestamps here that we've generated. They're current. We have our vehicle count. We can see that it's oscillating, and as well as our vehicle speed. And here we already see an anomaly type, because the idea being here that we have already made some classifications already that we have put into Milvus. And so this is kind of what the data looks like that we might be writing into Milvus, so that when we get new data that just includes like vehicle count, average speed, and maybe even video data, we can then use that to perform a similarity search and then determine, do we have an accident or do we have another type of anomaly? I think the three type of anomalies here, uh, accident, construction, and one other one that I can't remember. And then next we're just going to explore the data so we can kind of see what it looks like. So here we have the blue line representing our vehicle count and the red line representing the average speed at different timestamps. And so this is also how we'll write and query pandas data frames to InfluxDB. So I mentioned earlier how you would query data from InfluxDB, which is what I would imagine you would do in this use case. Query it, and then you'd have your data frame directly here instead. And the way that you would do that would be to query it right here with pandas, but the way that you would write it is to just include your bucket name, pass in your data frame directly as your record. You can include a data frame measurement name. That's the same thing as basically specifying what you want your table to be called. And I called it just generated data. And you can include any data frame tag columns you have. A tag is just where you have your metadata about your time series data, but this is totally optional. This is just kind of more for the user to organize their data. It doesn't matter on the database side, so you really don't have to worry about it. And then you can specify which column your timestamp is actually in, which is in our timestamp column. Or alternatively, if ever your data frame, the timestamp is in the index, then you can just write it directly without specifying because that's the default. And then to query it, you would query it from SQL, and you would say like select all the data from the last 90 days or 9 hours, whatever it might be, and then use the query method, pass in that query, return the mode pandas, and then you would ideally return some data that looks like this minus the anomaly detection column. Okay, so now that we're there, we're ready to actually go ahead and create some sensor vector embeddings. And so this is like where we're going to actually start grouping our data into time windows. And the purpose of that is to prepare it for the vector embeddings. So what we're going to do is use a window, a sliding window approach, where we're going to use a window size of 24 steps, a window size of 24, and a step size of 10. So that means that each window contains 24 data points, and then the next window starts 10 points later. And we're going to output a new data frame that's going to be called embeddings underscore data frame, and that contains the start and end times for each window and the corresponding average speed vectors and their anomaly type. So here I'm just defining those windows, and then here I'm iterating through the windows and extracting the column values for each one. And then here I'm creating a new data frame for that collected data so that I can create a embedded data frame that looks like that. So here we basically have our vectors where we're now having these sliding windows of time series data with our start and stop times. And so now I have the task of normalizing the sensor values. And the purpose of normalizing your sensor values is to take your average speeds and make them a value between 0 and 1 for consistent comparison analysis. So basically, if all the values in a vector are also identical, then the normalized result would all be a vector of zeros. Otherwise, each value is going to be scaled based off of the minimum and maximum values in the vector. So essentially, the normalized vector is basically where we take the original value, the average speed, and subtract it from the minimum value in the vector in the list, and then divide it by the max value minus the minimum value. And this ensures that the smallest value in the list becomes 0 and the largest value in the list becomes 1. We also do some edge case handling in case we have to divide by 0. But what's the point of this? So basically, normalization is really crucial when you're working with vectors like Milvus and working with vector databases like Milvus to ensure that you can compare your time windows effectively, because different time windows might have different scales or different average speeds. And so what we're really trying to do here is not just determine whether or not a particular value is out of the ordinary, because we might be comparing what traffic looks like across a bunch of different parts of the cities with different time zones, speed limits, etc. So what we really want to be doing is normalizing our time series data so that we can focus not on the absolute value of our speeds and our time series values, but the actual shape. So we can be comparing what the actual shape of a vector looks like. Because essentially when we take our time series and we're looking at a chunk of it and we put it in that multidimensional space, we're creating a multidimensional shape for that time series. And so without normalization, if we kind of compare vectors with vastly different ranges, it wouldn't necessarily yield meaningful results. So hopefully this also improves our search accuracy, especially because we're relying on distance measures and search measures like Euclidean distance. If the vectors aren't normalized, then really large values in one vector would disproportionately affect the search results. So normalization also helps us ensure that each vector contributes equally to the similarity calculation and computation. And then, like I mentioned, it also handles intentional variability, but also just any real world variability. Some periods of traffic might have really low variability if you have steady flow, while other might have really high variability if it's stop and go traffic. So normalizing the vectors also helps balance these differences. And so we're creating this function basically to do that to our vectors where we're performing that math there. And now we can see that we have our time series data from a scale of 0 to 1. And then last but not least, we need to also convert our data to timestamps and our timestamps to Unix. And the reason that we need to convert them to Unix is because Milvus doesn't allow you to write timestamps, and specifically we need a format that's useful for performing searches in those queries. So we're basically casting our timestamp to Unix and casting that to an integer. And so there we have our Unix precision time. And now we actually need to convert our embedding data frame into an entity so that we can actually prepare to write that to Zillis. And so basically we're iterating through every row and column in our data frame to do that. And so this is what a vector would actually look like, where we have our vector field, and that's all of our normalized time series data. We also have our start time and our stop time and our anomaly type. And so now we're ready to go ahead and store our entities into Zillis. So here we specify the vector field, and that's the normalized vector of average speed values. The start time field and the stop time field are just the stop and end times for each window, and the anomaly type field is going to be the type of anomaly. So here we define the schema for our collection by defining those and as well as their types. And then we create a schema collection, and then we define our collection and give it a name. And we check whether or not the collection already exists and make sure there aren't any conflicts. There shouldn't be if you just pulled the repo and spun up a Docker container for the first time. And then you specify your index parameters as well to perform the search on. And we'll be using L2 specifically, which is the query vector for Euclidean distance. That being said, Milvus has a bunch of other types for the embeddings. There's inner product, there's cosine similarity, so you have options. But I think Euclidean is usually what most people start with. And so now we can see that we have a successful insertion of our data, and we also can list our collection, which we named example collection, to make sure that we have in fact created it. So now we're ready to actually go ahead and create or perform our similarity search. So here we're going to search for vectors in Milvus that are most similar to our query vector using that Euclidean distance. So the line vectors underscore to search equals data underscore to search one vector field. This line is going to specify the vector that we want to use as the query vector for the search. Specifically, we're selecting the second vector from the data to insert list to perform our search, which was generated earlier. And it just represents the average speed that we had before. So we can see that because we used the same vector that we already wrote into the collection as our query, that means that we're looking at literally the same values. So it makes a lot of sense. This is very confirming to us that in fact our similarity search is working as expected because we have a distance of 0. And then similarly, we have some higher distances for the vectors or the time series data that came right after. And then I'm also listing some of those IDs and returning them as well so that I can go ahead and graph the comparison of some of our vectors that we searched for. So the top 3 results that came back. And we can see that our search vector is the same. It's overlapping with our first vector because it is the same vector. So of course, it's going to return, the same vector to us because it performed the search correctly, and the one with the closest similarity is the same one. And then we see some other time series data that it brought back to us that was similar. And you can see there's definitely areas where the time series, like the trends are kind of similar. Of course, when we can perform a mean absolute error to quantify some of the similarities between, let's say, our search vector and vector 2. And when we do, we actually get a pretty high mean absolute error. So this is for the second most similar result that it's returning. And you might go, oh no, why? Why is that so high? But if you remember, we're generating completely random data. So this is actually also confirming, because we wouldn't expect, if we are performing a similarity search across random data, it'd be like statistically very improbable that we'd return, you're not supposed to, it's supposed to be random, that we'd return data that is also similar. So this is confirming in 2 folds that the first vector that's the same as the one that we're querying for is returning a distance of 0, and that the other ones that are random are returning a mean absolute error that's pretty high. That indicates that they are not similar because they are random data. So this kind of just really simple tutorial just walk you through how you can convert time series data into a vector. Try it out for yourself, get a feel for it. Instead, I would recommend that you actually include your own time series data and then perform some similarity searches and see how there are actually some similarities in the overall trends of your data, and being able to actually effectively collect and almost sort of classify some of the shapes of your time series data. And then last but not least, just good protocol is to, if you're not going to continue using that collection, to delete all collection that you have and disconnect from the database. So yeah, so that's essentially the demo there for how to do that. And I'll briefly walk you through, this is just kind of an FYI, some fun other projects that you can do with InfluxDB in case this kind of encouraged you or got you inspired to work with some time series. So this one is called Saving the Holidays, and basically it's an example of using HiveMQ with MQTT data and Quix to look at some machine data from a factory floor and perform some predictive maintenance on it. And what's cool about this project is that it also leverages Hugging Face and allows you to scale this project and this architecture for a real world use case. So while you can all run this locally, you could easily use this same architecture for your own projects. And it goes through, classifying complicated anomalies with ANNs, which are also used in vector databases for classification. So it's kind of a cool overlap. I talked about this project already, so I won't go through that. And actually, we're getting short on time, and I want to give people time to go ahead and ask questions. So I will just go ahead and just talk about some resources before we finish here. So the first one is that I want to encourage you to sign up for Influx Data for cloud. We have a free cloud trial. I showed, what the UI looked like here, and go ahead and get started really easily writing any data with Python or a variety of other methods. Then we also have our blog, which is a great resource if you want your preferred way of learning is through blogs and not webinars. There are blogs for almost every project that is in the GitHub org Influx community, so you can always look there and find corresponding blog posts in our blog. Our documentation is great. We also have InfluxDB University, and our community Slack and forums is a fantastic resource for asking any questions that you might have about all things time series and InfluxDB. So with that, I'll leave the floor and ask, do we have any questions?
Thank you very much first. Oh, that was actually very interesting. Thank you also for the cool demo. We have so far two questions. So one, which is generally we would get an embedding model to generate the embeddings, which are then saved in a vector database, to do similarity search. For time series data, how is the process covered? Could you spend some time on that?
I personally haven't used an embedding model to generate that. I think this is kind of like what you could use instead of a embedding model.
Hmm.
I think embedding models are oftentimes used for much more complicated unstructured data when you have things like video and text and um, things where you need to like perform complex extraction like that. But um, this is what I've found for time series specifically.
Hmm. So for time series, you'd say actually we don't need embedding models directly, right?
Yeah, I'm not sure. I haven't used
Yeah.
one. Yeah.
Okay, cool. There was another question that got deleted. Uh, but it's like I have one as well. Also, first, like a friend of mine would be very happy because he is creating proteins using generative AI and vector search. And it seems like he has a lab, and it seems like with Influx, you can have detection, for example, when you have problems in the labs. So I might give him a word about that. The question is back. So in the columns, if I have number entries, those should be fine. But what if the entries are some text?
Yeah, I think you're gonna have to then use an embedding model for the text specifically, and then combine them.
Okay, and I'll ask one on my end. So what other tools can be used for data processing, anomaly detection, or forecasting within Flux?
Oh, sure. I can actually go back, talk about some of those. So actually, one second. Give me 1 second to just
Hmm.
uncomment some slides here. Oh no,
Lost the slides.
I know I lost them too.
Thank you.
So we recommend a lot of different tasks. The first or tools for InfluxDB specifically. One would be Quix, which is a streaming platform that's all built on top of Kafka for data processing, and it's all abstracted with Python and a UI, so you don't actually have to worry about configuring Kafka. But highly scalable. They have a cloud version, um, and they're releasing a community edition as well. Um, and that's what this whole project is based off of. Uses Quix to use source plugins for both MQTT to get data from an MQTT broker, as well as employ. Quix has plugins for Hugging Face as well, so that you can apply any machine learning models that you might want. There's also Mage, which is they consider themselves to be the open source alternative to Airflow, and it's also an open source ETL tool that's very easy to use. And there are in that same organization some examples for how to do anomaly detection with InfluxDB and Mage using half space trees, for example. So you can try that out for yourself as well. There's also things just like AWS Fargate. Um, you know, you can just use that to do any sort of task scheduling that you might want to do. I would imagine that would be more for some things like micro batching or downsampling or creating micro batch forecasts instead. But again, you can try that for yourself. And then ByteWax is another alternative. It's another open source tool that's used for data processing pipelines. And I actually did not include a link for that, but if you look at the blog and you just search for ByteWax and InfluxDB, or you look here, you can also find a project for that to use ByteWax with InfluxDB for some data processing. And then can also recommend Kafka and Faust, using those together. Faust is also open source. It's community maintained, um, but you can use it to, you know, do any sort of stream processing that you might want and include any sort of anomaly detection or forecasting that you might want to include. And then in general, there's also one fun thing that's happening, obviously, in tech right now, and in machine learning and AI is LLMs, and that doesn't exclude people using language models for time series specifically, where instead you're tokenizing the time series instead of words. And so there are a bunch of different models that do this. Google has one. Um, there's Chronos. There's like 5 different ones right now, and I can't remember all of their names. Tiny Pixar LLM is another one, and Autolab has one. But basically, those are really cool to look into because they provide zero shot forecasting, which means that you don't have to train your data at all, and you can just simply borrow those weights from Hugging Face, apply them to your time series data, and then just get a forecast. So it's kind of like you don't have to have any forecasting knowledge or expertise. The only hard part about using them is actually using them because they require very specific environments, and there isn't a lot of documentation around like how to deploy and or use them. So yeah.
Cool. Thank you. And we
Mhm.
have another question, which is very interesting. Would this be useful for crypto prediction? Would you say
For what? For what?
crypto like Bitcoin or anything prediction,
Oh, I mean,
or like financial prediction in general? I would say.
yeah, I mean, I think that's the idea between time series LMs. If you look at they're also they really perform well if you are doing multivariate analysis. So if you were looking at, stock trends and NLP and bunch of different time series data altogether, that's where they really shine. If you're trying to do short-term univariate time series predictions, that's where statistical methods still have an advantage. But the fact that you can now use some of these models to um, just forecast, like, it's just wild that there's a model that can forecast very accurately any type of time series data if you just give it like a good enough window and your data exhibits some sort of seasonality,
Hmm.
and it works across all sorts of domains and all different types of time series. So they're looking really promising, and we've definitely reached a point in the time series space where machine learning methods are consistently outperforming statistical methods. Now, whether or not you have like the team and the ability to like maintain that, and it's worth it to you, and there's like the cost benefit analysis of all that maintenance and that domain expertise versus using a statistical method that's easy to use and doesn't require a lot of resources, like that's a whole other issue. But
Hmm.
yeah, it's interesting stuff in the last 2 years. So
Okay, cool. Thank you. And
mhm.
last one as well to conclude. How did we combine the analytical results from time series data with the results from vector search? Is it based on the timestamp of the matching results from both sides? I guess that's
Oh,
referring to
it
your
was
demo.
it was based on the actual shape of the time series. So when
Okay.
we normalized the data, we basically created a multidimensional shape based off of that time series, and then we said which of our new search or new time series looks the most like that previous shape based off of the Euclidean distance.
Okay.
But then we included the timestamp in the index so that we could say like, oh, this anomaly is happening at this time. It's just like additional information that might be useful to the end user.
Okay, cool. Thank you.
Mhm.
I think we don't have any more questions. Thank you again, Anais, for the presentation. That was really cool. Also, kudos on the demo. Thank you,
Yay.
everyone else that attended. We'll share the recording in a couple of days. It will also be on YouTube, and then you can follow us on socials anyway. Thank you, everyone. Have a lovely morning, afternoon, evening, wherever you are. Bye.
Bye. Thank you.